All right, hello, and welcome to the Sunday/Monday edition of Math 341. This marks the beginning of our last week of instruction on new material, and the week following I will come up with some kind of plan for holding a kind of WebEx type of office hour thing, but I will inform you of that via email. And of course, your last assignment 10, is posted and outstanding. Let me see what else. I think that's about it. There will be an email forthcoming about exam details in the next couple of days. Yeah, I think that about covers it. Anyhow, I just realized that I absentmindedly erased exactly the thing that we were supposed to start by talking about today, so I will put it back up there. So, the last thing I had on the board was related to our discussion of uniform continuity, and it says the following. If you have a function f defined on a closed and bounded interval a, b, and if it is continuous on the entire closed bounded interval AB, that is, it is continuous at every point in AB, then f is something stronger. It is uniformly continuous on that same domain, the closed bounded interval from A to B. Okay, so continuity implies uniform continuity in the special case that the domain is the closed bounded interval. 1 second. Hello? Yes. I'm in the middle of my lecture. Call me back in an hour. Well, I told my son to call me in case of emergency, and that was definitely not an emergency. Okay, my apologies. Proof. It is a proof by contradiction. Okay, so suppose then that f is not uniformly continuous on AB. Okay? So what we will then want to do is take this assumption and somehow find a way to then prove that f is also not continuous at some point in AB. Okay? So the initial assumption is that f is not uniformly continuous on the closed bounded interval AB. So let's recall what that means. Okay. Thus, so this is one characterization of the failure of uniform continuity. There exist sequences say u sub n and x sub n in the closed bounded interval a comma b, and some epsilon naught greater than 0, such that what happens? Well, on the one hand, the elements of these two sequences are getting closer and closer together, which we express by saying that the absolute value of xn minus un tends to 0, yet the distance between the values of f at xn and un, they stay far apart. So this is the failure of uniform continuity. Yet the absolute value of f at xn minus f at un, that's greater than or equal to epsilon naught, which is of course bigger than 0. Okay, and as I tried to explain, waving my hands a little bit, last time, in general, of course, neither xn nor un has to be a convergent sequence, right? I mean, these two guys can wobble all over the place in this domain a comma b, provided that they are getting closer and closer together. And you can easily imagine sequences that don't converge that nevertheless get closer and closer together. What we're going to do is exploit the fact that both sequences, right, so we need to exploit the structure of the domain. It's the domain combined with the continuity of f that somehow makes the magic happen. So we're going to exploit the fact that both xn and un belong to this closed bounded interval a comma b, and what that means is that although xn, say, may not converge, there's certainly, it's a bounded sequence, right? And so the Bolzano-Weierstrass theorem says that xn has to have a convergent subsequence, okay? So, by Bolzano-Weierstrass, there exists a subsequence xnk such that xnk converges to C, and that C belongs to our interval a comma b. Okay? All right. So what we're going to do now is use the fact that xn minus un converges to 0 to show that, in fact, it must also be the case that the same subsequence for the u's, the u sub nk's, they also converge to C. Okay, so let's do that now. So, given some epsilon greater than 0, there exists a capital N of epsilon, a natural number, such that the distance from un to xn is less than, say, epsilon over 2 if little n is greater or equal to this capital N of epsilon. Okay? So this is just using the fact that this sequence here converges to 0. Okay? Also, there is, let's say, a capital K of epsilon. Well, I should say a natural number such that two things are true. such that little n sub capital K of epsilon is, say, greater than or equal to capital N of epsilon, and the distance from x sub nk to c is less than epsilon over 2 if little k is greater or equal to capital K of epsilon. Okay? So, whoops. Screen's gone dark there. Okay. All right, so first we use the fact that this sequence converges to 0 to get this statement here, and then we use the fact that our subsequence, these x and k's, they converge to this number c, okay? And to express that, we find some capital K of epsilon such that when the little index, little k, is bigger than or equal to k of epsilon, we certainly get that the distance from x and k to c is strictly less than epsilon over 2, but we also get, as a kind of bonus that we will need, that n sub capital K of epsilon is bigger than or equal to this n of epsilon. And that's because in a moment here, we're going to apply a triangle inequality. So what I will say is now, if little k does indeed happen to be bigger than this capital K of epsilon, we compute. We want this to be small. We're trying to show that the same subsequence of UNKs also converges to this point C, which makes sense, right? The XNKs converge to C, and the UNKs and XNKs are getting closer and closer together, so it makes sense that the UNKs should converge to C. We just have to write down the details, and so to do that, we will do the usual give and take argument. So we will subtract and add x sub nk, and finally subtract c. Okay, and then we will group together these two guys and group together these two guys and apply the triangle inequality to see that this is less than or equal to the absolute value of UNK minus XNK plus the absolute value of XNK minus C. All right, I'm going to erase the rest of this now. Okay, and now little k is bigger than or equal to capital K of epsilon, which means that each one of these little indices down here, n sub k, okay, those are both bigger than or equal to capital N of epsilon. That was part of the way in which we chose this capital K of epsilon. So this thing here is less than epsilon over 2. Similarly, over here, that capital K of epsilon was chosen so that if little k is greater than or equal to capital K of epsilon, this quantity here is also less than epsilon over 2. The whole thing is epsilon, right? And that proves that if little k is greater than or equal to capital K of epsilon, then the distance from UNK to C is strictly less than epsilon. So UNK converges to C as well. All right, so now we have these two subsequences, XNK and UNK, and they both converge to C. Right. So we also have that, as a basic assumption, our function f is continuous. So by continuity, continuity f of x and k and f of u and k, they both converge to the same thing, namely f of c. Right? Well, if they both converge, thus for our epsilon naught greater than 0, so remember, this epsilon naught is that number greater than 0 such that f of x and k minus f of u and k, that absolute value is always greater than or equal to this epsilon naught. Right? The function values are staying this far apart. Okay? On the other hand, for this epsilon naught greater than 0, there exists, say, a k1 of epsilon naught such that what? Such that f of x and k minus f of c is less than epsilon over 2 if little k is greater or equal to k1 of epsilon naught and there exists another natural number, k sub 2, say, of epsilon naught, such that f of u and k minus f of c is also less than epsilon over 2, but now if little k is bigger than or equal to this new k2 of epsilon naught. So if little k is greater or equal to capital K2 of epsilon naught. All right, so all I'm doing here is writing down the definition of what it means for f of x and k to converge to f of c, and for f of u and k to converge to f of c. All right? And again, I'm going to use a little triangle. Whoops. I apologize. These should both be epsilon naughts. That's important. Right? And so what I'm going to want to do is try to show, so f of x and k and f of u and k, they both converge to the same number, this f of c, right? And therefore they should be getting arbitrarily close together, which will violate this condition that those function values should stay far apart by this amount here at minimum, okay? Right, and so again, this is going to be a triangle inequality thing, and again, I'm going to need for this statement, this inequality, and this one here to be true at the same time, right? So I will, to that end, set capital K of epsilon naught to be equal to the max of K1 of epsilon naught and K2 of epsilon naught. Okay? And now finally I will be able to generate my contradiction. I will be able to show that the function values for some x and k and u and k, those are at distance strictly less than epsilon naught, which violates our original assumption and disproves. will give us our contradiction. Thus, for little k greater or equal to capital K of epsilon naught, if I look at f of x n k minus f of u n k, that's going to be, again, this is a triangle inequality argument, so it's going to be less than or equal to the absolute value of f of x n k minus f of c plus absolute value of f of c minus f of u n k. And we just finished showing that each one of these two quantities is less than epsilon naught over 2. Okay? And this contradicts, this contradicts our original assumption. All right? This contradicts f of x n k minus f of u n k greater or equal to epsilon naught. And that completes the proof. Okay? All right. So that proves that a continuous function on a closed bounded interval has to be uniformly continuous. Okay? There are lots of other interesting things that you can say about uniformly continuous functions, both on closed bounded intervals and on other intervals. We don't really have time to cover a huge number of these consequences, but there's one really important one that I will mention here without proof. The proof is kind of involved, and there's no proof that really isn't a little bit tricky. But the result itself is really nice and extremely useful. So if you are an engineer or really engaged in any kind of practical approximation of some theoretical functions, the following theorem will make your life easier. The theorem, in fact, it has a name. Once again, Weierstrass, busy guy. It's called the Weierstrass Approximation Theorem. Okay? And it says the following. Let f from a closed bounded interval a b to r be continuous given epsilon greater than 0, there is a, so the idea is that this function f, if it's continuous on the closed bounded interval, it is approximately, in an arbitrarily good sense, a polynomial. Okay, so there is out there some polynomial, in this case we'll call it, there is a polynomial, say capital, or not capital, little p of epsilon of x, such that the absolute value of f of x minus p sub epsilon of x is less than epsilon for all x in the entire domain simultaneously. okay? So that any continuous function on a closed bounded interval can be approximated arbitrarily well by a polynomial. And of course, if you are trying to compute things, then polynomials are nice because it's clear how you ask a computer, say, to compute a polynomial. It's just a bunch of simple floating point operations, multiplication and addition. And so this can be a very useful way to get a good idea of what a function f looks like. Now, what is not really covered here is, of course, how you get this polynomial, right? And as an approximation theorem, this is only as useful as the polynomial is computable. So, if in order to approximate some relatively simple looking function, you need a polynomial of degree 74 million, that's not as helpful as needing a polynomial of degree 5 or something, okay? So that's where things like Taylor series and so on come in. I mean, you don't just want a polynomial approximation, you also want a polynomial approximation that's relatively easy to compute. But this does tell you in principle that if you want to get as close as you like to your function f, then you're going to be able to do it with a polynomial, okay? So like I said, we won't prove this, but it's a very nice theorem, among many, that Weierstrass has to his credit. Okay? And so that concludes section 5.4 on uniform continuity. All right. Section 5.4, or sorry, 5.5, on something called continuity and gauges. I don't really think this is kind of a standard topic to cover in a course like this. I don't know why they do cover it, but we're not going to. So this will be omitted. It's already been omitted from the homework. I'm telling you here that it's omitted from any consideration in this course. Okay, you don't have to know anything about anything from section 5.5. Right, that's omitted entirely. And we will move straight on to the last section in chapter 5, section 5.6, which is on monotone functions. And their inverses, and some other nifty things about them. So one particularly neat result that we'll cover in this section is so we've clearly seen some examples of functions that can behave really, really badly when it comes to continuity. So we've got this example, the function that's equal to 0 at every, say, irrational number and equal to 1 at every rational number. And that function is continuous absolutely nowhere, and is a hot mess, okay? And it's pretty clear there's all kinds of sort of jump discontinuities in there. Monotone functions, that is functions that are either increasing, always going up, or always going down, even if you don't assume that they are continuous, you just assume that they're monotone, it turns out that they are necessarily not super horribly behaved. And one way to quantify that we'll see is that if you have, say, an increasing function, then it is going to have, over a given closed bounded interval, it's going to have at most countably many points where it is discontinuous. Okay, so contrast that with our example of a function which is equal to 0 at every irrational and 1 at every rational, that thing, we proved, was actually discontinuous literally everywhere at every real number, and so is discontinuous at an uncountable number of points. But we will be able to show a general result which says that if you have a monotone function, say an increasing function, then yes, it can still be discontinuous. I mean, if you want, you could think of a function which is 0 up until you get to 0 and then jumps up to 1 for the rest of the time. But it can only be discontinuous at countably many points over a finite interval. Okay? So that's one neat thing that we'll discover. So let's start. Let me clear the board here and just start with the basic definitions. So we'll start with a general domain. So f is a function from A to R. This is monotone increasing if f at x1 is less than or equal to f at x2 whenever x1 is less than or equal to x2. F is strictly increasing if this inequality here for the function values, come on computer, if this inequality for the function values is a strict inequality, okay? If f at x1 is strictly less than f at x2 when x1 is less than or equal to x2. Okay? So that's an increasing function and a strictly increasing function. Then, as you might imagine, there is an alternate notion for decreasing. So let's just replace things here. So f from A to R then is instead monotone decreasing if f at x1 is instead greater than or equal to f at x2 when x1 is less than or equal to x2, and f is strictly decreasing if f at x1 is strictly bigger than f at x2 for x1 less than or equal to x2. Okay? So probably this notion is familiar to you, but there you have it. There's the definition. Okay, what did I want to say next? Sorry. I'm going without notes so far here. Right. So let's prove a little theorem. So this theorem ultimately is aimed at giving us a characterization of when a when an increasing function is continuous, and similarly when a decreasing function is continuous. Okay? So theorem. So let's let f be a function from I to R increasing. So f is an increasing function where I is an interval. Okay, it doesn't have to be a closed and bounded interval. It could be a half open interval, half closed. It could be an infinite interval. Okay, just some kind of interval. Suppose C is not an endpoint of I. Then two things are true, so we have a way of characterizing the limits from the left and the right of this monotone function as we approach this number C. So, 1 says that the limit as x approaches C from the left of f is equal to the supremum of the set of function values of f. Function values for, of course, values of x that belong to the domain, and which are, moreover, strictly less than C. Okay? So you look at all the values of the function for values of x that are strictly before this point C that you're interested in. That forms some non-empty set of real numbers, which, it turns out, as we shall see in the proof, is bounded above by f at C, and therefore has a sup, and you can show that that supremum, in fact, has to be exactly the limit as x approaches C from the left of your function f. And similarly, the limit as x approaches C from the right of f is equal to the infimum of all the function values f of x, where once again x is drawn from the domain I, but now x instead is strictly greater than C. Okay? So it tells you that the limit of the function f, the monotone increasing function f from the left, is given as a supremum of function values, while the limit of the function f from the right is given as an infimum of function values, which hopefully kind of makes sense. Before we get into the proof here, let me just quickly draw you a picture. Let me just quickly draw a picture up here. Right, so the idea is that you can easily imagine an increasing function which is nevertheless not continuous. So here's your f of x, and maybe this is our interval I. Okay? And so the limit, and this point here, I guess, would be C. And so the limit as x approaches C of f of x does not exist. Right? There is no limit. Right? However, the limit from the left and the limit from the right, they both exist. And it seems, hopefully, to me, pretty clear from the picture that to figure out what this limit is, you just have to look at the values of the function prior to this point C, hence the x less than C, and take the sup of all those guys. Whereas, to find this limit here, You just look at all the values of the function after the point C, hence x greater than C, okay? And then you take the infimum. You slide down backward toward that point, okay? And then, of course, you know, if everything works out perfectly, these two limits will be equal, and the function will be continuous at that point. But this is the basic idea. Okay, so let's prove part one. Part two is a similar proof. Okay, so proof. So we will show part one. Two is similar. Okay. All right, so we want, let's remind ourselves here, we want the limit as x approaches C from the left of f to be equal to the sup of all the function values, f of x, where x is in this interval I, and x is less than C. Okay? Well, if you want to show something is equal to a sup, you had better know that that supremum exists in the first place, right? Which means that we need to know this set here is non-empty and bounded above. So C is, here's where the not an endpoint thing comes in. So C is not an endpoint of I. So there exists x in I, x less than C, and so this set f of x such that x belongs to I and x is strictly less than C is not empty and moreover it's bounded above. And why is that? Well, it's bounded above because all of these function values come from values of x that are strictly less than C, and the function is increasing, right? Meaning that f of C has to be bigger than or equal to f of x for every one of these x's, right? So it's non-empty and bounded above by capital F of C, all of which implies that it has a sup equal to, say, capital L. All right? So at the very least, this right-hand side of our equality exists, right? It is some real number. Now we have to show that it's equal to the limit as x approaches C from the left. So let epsilon greater than 0 be given. It follows that, well, of course, L minus epsilon is not an upper bound for that set. So that means in particular there exists some y of epsilon belonging to the interval I, y sub epsilon strictly less than c, such that the function value at y epsilon, such that f of y epsilon, of course, satisfies that it is less than or equal to the sup, but also is strictly greater than L minus epsilon. Okay? Now, we want to prove a statement about the limit of f, right, as x approaches c from the left, which means that given an epsilon greater than 0, we need to find a delta. We need to know how close to this point c we need to be in order for our function value to be within epsilon of what we think the limit is, namely this supremum L. Okay? And it's this y epsilon that will tell us what that delta of epsilon should be. The distance from c to y epsilon is what we should take for our delta of epsilon. So let's set delta sub epsilon equal to c minus y sub epsilon. Then, if you have a generic point y which satisfies the pair of inequalities that you find at the end of the definition of the limit from the left-hand side, right? Namely that the fixed point c you're approaching minus the generic point has to be, well, greater than 0 to tell you that c comes, or y comes before c, but also has to be strictly less than delta of epsilon to tell you that c and y are very close together, right? And if you have this situation, this implies that y, right, I guess is greater than y epsilon. So L minus epsilon strictly less than f of y epsilon, which is less than or equal to f of y, which is less than or equal to L, all of which implies that f of y minus L is less than epsilon, right? You've sandwiched this f of y in between L and L minus epsilon, meaning the distance from f of y to L must be strictly less than epsilon. And that's exactly the statement of what it means for the limit of the function f as x approaches c from the left to be equal to L. So that does it. All right. So the proof of part 2, like I say, is similar, okay? And the point is that what this allows us to do is characterize exactly when an increasing or decreasing, when a monotone function is continuous in terms of the infimum and supremum of two fairly obvious sets. The other thing that's going to happen in the next class is that we're going to consider and give a name to the difference between those left and right hand limits. Because the difference, if you remember my little picture, just quickly, here's a monotone increasing function once again. It's not continuous at this point here, right? And so the kind of discontinuity you get is always one of these little jumps, right? And if you take the difference between the limit from the right-hand side and the limit from the left-hand side, what you're going to get back is the size of the jump. Okay, so we're going to give that thing a name in the next class, and we're going to use the idea that, you know, as you pass through an interval, I mean, how far you get. You start at some point down here, you wind up at some point up here. If you put together all the jumps that you get in between those 2 points, they got to add up to something finite at best, right? And what that will mean is that there can be at most countably many non-zero jumps. And that's going to tell us that there are most countably many points over a closed interval where a monotone function can be discontinuous. All right, I'm a little over there, so I will cut it here. Wash your hands, and I will see you on Wednesday.